In this video, we will learn how to correctly specify TP class CTs. In the last video, we saw that TP class CTs can become very large. That is why it is so important that the design parameters we specify are as accurate as possible. Overspecification makes the CT oversized, underspecification risks saturation and relay misoperation. So accuracy in specification is critical. Before we begin, I strongly recommend watching the previous two videos in this series. The first video explains the basics of transient performance CTs. The second video explains how to size TP class CTs correctly. If you watch those two first, everything in this video will make much more sense. Alright, let us continue. To specify a transient performance CT, we must know the duty cycle the CT will experience during a fault. This duty cycle determines how the flux builds up in the core, and therefore how large the CT core must be. IEC 61869 defines two types of duty cycles: the single energization duty cycle and the double energization duty cycle. Let us start with the single energization duty cycle. To define this duty cycle, we specify only one parameter: the specified time to accuracy limit, the duration for which the CT must remain accurate. Now let us move to the double energization duty cycle. A double energization happens in applications like auto reclosing. To define the double energization duty cycle, we describe the first energization, the dead time, and the second energization. For the first energization, we specify the time to accuracy limit for the first fault and the duration of the first fault. Then we specify the fault repetition time, TFR. This is the dead time between the first clearing and the second energization. For the second energization, we again specify the time to accuracy limit for the second fault. This accuracy time can be different for the first and second energizations. If you want to understand the reason, please watch the previous video in this series. These parameters together form the complete double energization duty cycle. They allow the manufacturer to understand how flux builds up in the core across both energizations and to determine the correct transient dimensioning factor, KTD. Now that we understand the duty cycle definitions, let us look at how to specify a TP class CT. There are two methods in IEC 61869 Part 2. The standard specification method and the alternate specification method. First, let us look at the standard specification method. This method is used when one specific duty cycle, whether single energization or double energization, fully defines your protection requirement. In this method, you specify the following: class designation TPX or TPY or TPZ. The rated symmetrical short circuit current factor, KSSC. The complete duty cycle parameters we just learned. The rated primary time constant. And the rated resistive burden. These inputs allow the manufacturer to design the CT core so that it remains accurate for the defined duty cycle. With the standard method understood, let us now look at the alternate specification method. This method is used when one duty cycle cannot fully describe all possible scenarios. It allows you to specify overall requirements that cover multiple duty cycles. In this method, we specify the following: class designation. The rated symmetrical short circuit current factor, KSSC. The transient dimensioning factor, KTD. And to know how to calculate KTD, please watch the previous video in this series, where we explained it in detail. The secondary loop time constant, TS. It is needed for TPY cores only. And the rated resistive burden. A very important note here: do not mix parameters from the standard method and the alternate method. If you do, the CT will likely become oversized and uneconomical. Correct specification requires choosing one method and sticking to it. If you found this helpful, please like the video, subscribe to the channel, and share it with your colleagues.